In this video, we're going to continue our discussion about descriptive statistics. But in this video, we're going to focus on the majority of the graphs that we're going to talk about, and then we're going to talk about shapes of distributions. Let's start with graphs. First, let's talk about the graphs for nominal and ordinal variables. One of the most commonly used graphs for these variables are your bar graphs. Bar graphs are graphs of data that use bars of equal width to compare different categories of your variables, right? On your horizontal axis, you're going to have the distinct categories. Each are going to be a separate bar with space in between. And then your vertical axis is going to be your y-axis. That's going to have your reference to your frequencies or your relative frequency. Each bar is going to represent a category with its height corresponding to the frequency or relative frequency. So if I go back to a previous example that we've reviewed, which is about child care centers and the different types of permits that they have in the state of South Carolina. We've seen this data set before. This is the frequency table. Well, another way to visualize this frequency table is to use a bar graph. So each bar is going to be referenced on by the category listed on the horizontal axis, your x-axis, and then the height of each of those bars, as you can see, is going to be the relative frequency. And so I have this bar graph here. So it's very easy, maybe a little more easy to see that the license is the mode. The category of least frequency is the not licensed or exempt providers. And so you can gather a lot of information from this graph as well. Now, as I stated, in addition to using the frequency, you can also plot on your vertical axis as the height of your bars, your relative frequency, or you can actually do your percentages as well. And so I just wanted to show you an alternative here. My vertical axis, instead of being labeled as the number of childcare providers, we have the proportion of childcare providers that are in each of these categories here. So you can adjust this. If you wanted to put percentages here, you can put percentages as well. I do want to make note, a lot of time, especially in this day and age of data visualization, you'll see people organizing these charts slightly different. For instance, they may use, instead of just a general bar graph, they may have some ordering of the categories in descending order from greatest to least frequency in what we call Pareto charts or graphs. Okay, these are bar graphs where the bars still represent the individual categories, but they're arranged in order, in descending order of the frequency or the relative frequency or the percentage in each category. And so we see an example of that here. It's a lot better organized. You have it in order from least to greatest, so we can see the highest category, the smallest category. It's just easier to read. So that's bar graphs. That's one type of graph that we can use for nominal and ordinal data. We can also use pie charts. These are graphs that show the amount of data that belongs to each category as a proportional part of a circle. Hence the word pie. You can think of it as slices of a pie, each category represented as a slice of a pie. And the size of each slice corresponds to the proportion or percentage of that category in the data set. One thing to be careful about when you're using pie charts is that your categories must sum up to a meaningful whole. So if you have a scenario where you're trying to show data in a graph and your data are not oriented to where all of your categories represent part of a whole, you should not use a pie chart. For that example, where we have the permit type of child care centers in South Carolina, this will be the example of a pie chart. We have the different colors or slices of pie representing the different categories, and we have the different proportions or percentages of observations within that category as the proportional slice of the pie. One thing to note here is that bar graphs can really be used to graph either variable, whether they're nominal or ordinal, and whether the categories sum up to a whole or not. You can use a bar graph. It's more flexible. Also, bar graphs are more common, especially when it comes to publications. if you have a lot of categories. Now, with pie charts, you rarely see them in publications, and then they're limited because you can only use them when you have the data oriented in such a way that you have all of the parts that make up a whole. Again, they're less common unless you're using publications. So what we'll see most often in this course, if we're going to use a graph, a bar graph, or a graph for nominal or ordinal data, we'll use bar graphs. Now let's switch gears and talk about graphs for interval or ratio variables. There are more than this. Some of them include stem and leaf plots, or some people call them stem and leaf tables. There's also dot plots. And as we've talked about before, there's histograms, which we'll talk about a little more in detail in this video here. So with stem and leaf plots, our graphs, all of the values in our graphs are separated into a stem and a leaf. The stem includes the left part of the plot, and it represents the leading digits of the data values. And the leaves are the right part of the actual plot. And then they represent the trailing digits of the data values. These are very similar to histograms, but the difference is, and the convenience or the advantage of using stem and leaf plots is that we can see all of the original data values. So we'll see all of the numbers that are actually in our data set. Whereas when we look at histograms, we get just a distribution and not the actual values. Dot plots are graphs where individual data points are represented as dots along a number line. Dot plots are great for small to medium-sized data sets. And so that's the advantage here. You may see them used there. Let's look at an example of each of these with a small data set with a sample size of 20. It says, suppose an educational researcher wanted to analyze the test scores out of 100 points of a group of students in an intervention group. These are the scores here. What we can do is we can make a stem and leaf plot, and we can make a dot plot. Here is an example of the stem and leaf plot. You see that first column has the stem, the last column has the leaves, and basically we can separate each number so that the leading digits, so there's only one leading digit for most of these numbers, are the stem. So I have my stem 7 here, and the last digit is my leaf. So when I see this 1 here, it represents the number 71. When I see this 8 here, it represents the number 78. There are two 78s, which is why I have two 8s as leaves here. Notice the only values that are more than 2 digits are the values of 100 here. The leading digits, there's more than one leading digit. There's 1 and 0, which makes 10, right? So I have that here. And both of these have last digit of 0, which is why we see 2 zeros here. So this first 0 represents 100. The second 0 also represents 100. All right, we can see the distribution of this data set. Most of the scores are in the 90s. The lowest category is in 100. Not far behind is the 70s, so on and so forth. And so we can get an idea of the distribution of our scores, and we can actually see all of the scores. If we wanted to create a dot plot, we can draw a number line, and then we'll plot the values of the actual data above the number line, right? So this dot here, for instance, represents 71. And since I have two 78s, I'm going to stack the actual dots above the value in my data, in my dot plot. So that's why we see 2 dots above 78, so on and so forth. And so those are 2 examples of graphs that you can use to see your distribution of scores. What we'll probably most often use and see are histograms, right? So we talked about histograms before. These are graphs of quantitative variables that are composed of bars of equal width whose heights represent frequencies of observations. So these are bar graphs, right? They're going to have bars, but the difference here is that usually our bars are connected when we're talking about a histogram, and when we're talking about bar graphs with nominal or ordinal data, those bars were separated because those are different categories. Well, now our horizontal axis is going to be a number line as well as our vertical axis because we have quantitative variables. So our horizontal axis is a number line on the scale of our quantitative variable, and our vertical axis, our y-axis, is a number line representing the frequency. And of course, the height of these bars are going to be on our vertical axis. Remember when we saw this data from before, we had our classes of equal width. Those are going to be plotted on our horizontal or x-axis. They're going to make our bars of equal width. And then our frequencies are going to be the height of our bars referenced from our y-axis. And so if I go and try to look at a histogram of this data here, we're going to see. Now, I created this graph in a software called R, and the way R graphs it doesn't necessarily put your axes together. I could have done some work to do that, but I didn't do that in this example here. But do note that these axes, this starts at 0 and goes upward past 600, and then our y-axis starts at 0 and goes up to 1200 as described here. But we see our classes of equal width here, and then the height of our bars are frequencies that are given reference to our y-axis. So that 1117 would be approximately here. 1117 is a little over half there, and then the heights of the other categories will be given here. Now, if I continue, notice that all of these are connected, adjacent to each other, up until, and it's probably hard to see here, when I get to the values between, let's say, 551 to 600, right? That's because there's 0 frequency in this category here. So the only spaces that we're going to see when we have a histogram is when the frequency is 0. But this gives us a very good picture of how our data are distributed. We have a large portion of our sample that has between 1 and 50, a capacity of between 1 and 50. And then as we continue to get larger and larger, there's almost no childcare centers that have upwards of 400 on up to 600, 600 to 650 capacity. And so that is a histogram. We're probably never going to create these by hand. Most of our histograms are going to be created using computer technology. One thing about computer technology is that it is going to also create the classes of equal width. And so if you go in one statistical software, your histogram may be slightly different, or it may look slightly different from when you go to another statistical program, because they use their own methods in creating these classes of equal width. I didn't make any adjustments to this one. I just went to R, entered my data, and asked it to give me a histogram, and this is the one I believe it gave me. I don't think I made any adjustments. So be aware of that you may see different histograms based off of the way they chose their classes. With that histogram, we can come up with multiple shapes of distributions. And so remember when I said, we're going to report the mean and standard deviation if our data follow a normal distribution, and we're going to use the median and the minimum and maximum number as well as the range when our data do not fit a normal distribution. Well, and I said that there's more to come on this. This has to do with the shape of our distributions. Now that we have our histograms, it's easier to see different shapes of distributions. And so what we're going to do here is talk about some of the terms that we can use to describe the shapes of distributions that we'll probably most often see in educational research. When we're talking about shape, we're going to use 2 terms here. We can talk about whether the shape has one peak. These distributions are known as unimodal distribution. The prefix uni, it represents 1, and these are distributions with 1 peak. And then we can talk about whether a distribution is symmetrical or not. and use terms like symmetry and skewness, right? When a graph has symmetry, the right and left sides are approximately mirror images of each other. And then if we don't see that approximate mirror images of each other, where one distribution may contain all of the data on one side and very few on the other side of the graph, we're going to say that that distribution has some skewness or is skewed. I used the term normal distribution when I was talking about the differences in when we use the mean and standard deviation or the median and the range. And it has to do with this normal distribution here. We're going to have a whole week where we just focus on the normal distribution. I'll just give an introduction here. The normal distribution is probably the most popular distribution in statistics. It is a bell-shaped distribution, as you can see on this graph here. It is unimodal, which means it has one peak. All right, notice all of the data kind of increase until we get to the middle, to a peak, and then it decreases as we continue after that. So it has one peak, which we call unimodal. This distribution is approximately symmetric, meaning I have a line of symmetry, approximately, and the graph is approximately a mirror image of itself across that line of symmetry. Now, when we're talking about data, because we're going to be using our sample taken from our population, we're not going to have perfectly mirror images or perfectly normal distributions at that, or perfect bell-shaped graphs, right? There's a lot of subjectivity that can come into play when we're looking at these graphs here. We can see, if you go to geometry, symmetry means one side is congruent to the other, or, it's more technical than that, but in layman's term, that's what we mean. That means if I folded this left side of the graph over onto the right side of the graph, it would overlap perfectly. We're probably never going to see that in real life, or we will very rarely see that in real life, right? So I can tell that this is not truly a mirror image, but it is an approximate mirror image. And so since it is an approximate mirror image, we will call this a bell-shaped graph. That's probably a normal distribution. The last thing about this is that notice on the tail end of the graph, the ends of the graph, the couple of bars that make up the end of the graph are called the tails. So I have a tail on the left and I have a tail on the right. Notice that the tails aren't that far from the center on either side of the graph, right? So we call that this graph has moderate tails. And again, the term tail means the ends of the graph. Bell-shaped graphs, those are normal distributions for us for now. Now, let's go to those distributions that are not symmetric. And these distributions for us that are unimodal, they're going to be skewed, right? Well, one way that they can be skewed is to be negatively skewed. And the way I remember negatively skewed, well, before we get there, notice that it's unimodal. It only has one mode or one peak. It is asymmetric, but it has a left tail that is longer than the right tail of the distribution. And notice here, negative, if I were to draw a number line and zero were in the middle, the negative values will be on the left. That is one way that I remember negatively skewed. Think about a number line, negative values are on the left. We're going to have a longer left tail or longer tail on the left. That's negatively skewed. So most of my data are on the right side of the graph, where I have less data that's creating this tail on this longer tail on the left on the smaller values of that distribution. Positively skewed is in the opposite direction. Again, we are unimodal here. We have asymmetry, but I have a right tail that is longer. So most of my values in my data set take up smaller values. So most of the observations are small in value, where I may have some observations that are incredibly large. And so that's skewing my data. All right, I'm getting closer to explaining why for normal or bell-shaped distributions, we want to report the mean versus with skewed distributions or non-normal distributions, we want to report the median. Remember that the median is about position, right? It is the value that cuts that data set in half. It's the value that lies in the middle of ordered data set, right? So one of the things that we talk about when we talk about whether we're going to report the mean or the median is the fact that the median is not sensitive or highly influenced by values on the tail ends of the distribution. Okay? And remember, the tail ends are those values that are on the tails, right? If I think about any data set, the middle has nothing to do with the tail ends. So we say that our median is not sensitive to values on those. It's not a sensitive measure of the center of your distribution. But the mean, look at the way the mean is calculated. You actually take each value and the magnitude of those values actually help us to calculate the value of that mean. The values of the median only has to do with the positioning, right? It doesn't actually, it's not actually calculated in your median. So our mean is sensitive to values on the extreme tail ends of a distribution because we actually use the values in the magnitude of those values in that calculation. So the reason why we say that when we have normal or bell-shaped distributions, we can report the mean. The truth of the matter is we can report either the mean or the median because they're going to be approximately equal. But a lot of times we use the mean because we're going to use the standard deviation. All right. But notice that there are approximately an equal number of observations on the lower extreme end of our data set as there on the upper extreme end of our data set, right? And the mean and the median is always going to be equal to each other in the center. Those on this lower end, their magnitude are going to be offset by the magnitude of the observations on this other end. And since we have symmetry here, our mean and our median are going to be equal. All right. This is not the case when we have skewed distributions. Because the mean is sensitive to extreme observations, the mean is going to be pulled towards the longer tail of the distribution. And so when we have a negatively skewed distribution, most of our data values are on this side of that distribution, given by the taller bars. But there are a few numbers in that distribution that are going to be smaller, that are going to be making that mean smaller and smaller. And so while our median is in the middle of that distribution, all right, our mean is going to be pulled towards the tail. And so with negatively skewed distributions, the mean is less than the median. The opposite happens when we have a positively skewed distribution. Our tail is on the right, and so those larger values are going to increase the value of your mean compared to if they weren't there. And so we're going to have our mean being greater than our median. And so because our means are are influenced by those values that are extreme in our data set, when we have skewed data set, and that's going to happen when we have data that are not normal, we're going to want to report the median as a typical value or a value that's a measure of central tendency instead of reporting our median. All right. So now we have this here. This is why we want to report the median versus the mean. Means are highly influenced by extreme values, and those extreme values are more likely to occur in data that are not normally distributed, that are not bell-shaped. So if I see a graph that's skewed, report the median, minimum, maximum, or your range. Now, there are other distributional shapes. For instance, we looked at graphs that were unimodal. Well, there are some distributions data that when you graph them, you're going to get a bimodal distribution. Notice my data go up to this peak, go back down, and then they go up again to this peak and continue to fall after that. So there's two peaks here. There's two modes. So we have a bimodal distribution. This usually happens when you have data that has has individuals with differing values. Um, Let me just give an example. It may happen when you measure something like height or weight for individuals of different sexes, so males and females. You may see a bimodal distribution. Males in general are taller than females, and so you'll see two different distributions. That's an example of when we may see like bimodal distributions. Um, we also can have uniform distributions where this is a rectangular shaped distribution that doesn't have a distinct peak. And so this is what we call a uniform distribution. And we may see that ever so often when individuals are kind of just scattered evenly across the entire distribution. All right. Well, that is it with the different shapes. We know now the different graphs to use when we're graphing or using descriptive statistics to show our data. Bar graphs most often for qualitative data, and histograms most often for quantitative data. And of course, now that we have that information, we know why we want to use our mean and our standard deviation for bell-shaped distributions. And now we know we want to report our median and those other measures of spread for distributions that are not bell-shaped. All right, that's going to be it for this video. We'll see you during the next one.